All right, today we are diving headfirst into the amazing world of molecules. We're going to talk about the powerful connections that hold them all together. We're talking about covalent bonds.
I mean, it's a fantastic question, right? You've got your two hydrogen atoms, one oxygen atom. What's the actual glue holding them together? What stops them from just, drifting apart? Turns out the answer is fundamental to pretty much everything around us.
Well, the best way to picture it is like a friendly, cooperative handshake between atoms. This isn't about one atom snatching something from another. Nope, it's all about teamwork, about working together. And that handshake, that's what we call a covalent bond.
Okay, let's get into it. What is a covalent bond really? To get our heads around it, we've got to zoom way, way in and see how these atoms pull off the ultimate share. The key word, the most important word here, is share. When two nonmetal atoms cozy up to each other, they figure out that they can both get that stable, full outer shell of electrons just by sharing a pair. It's a total win-win situation for both of them.
Let's actually see this happen. We'll take hydrogen chloride. So first up, you've got your hydrogen atom with its one lonely outer electron, and then you've got chlorine with 7. The next thing that happens is their outer shells overlap. And finally, they each put one electron into the middle to form a shared pair. And here's the magic. That shared pair now counts for both atoms. So hydrogen gets its full shell of 2, and chlorine gets its full shell of 8. Boom, a perfect, strong bond. Okay, that's cool, but how can we, predict and draw these things ourselves? Well, think of it like having a molecular blueprint. There's a set of really simple rules that let you build pretty much any simple molecule you can think of. And the logic behind it is it's beautifully simple. The number of bonds an atom is going to form is just how many electrons it needs to get a full outer shell. That's it. So carbon, it's in group 4. It needs 4 more electrons, so it makes 4 bonds. Oxygen is in group 6. It needs 2 more, so it makes 2 bonds. See? Simple. All right, let's put these rules to the test. We're going to build a molecule of ammonia, NH3. So the formula itself tells us what we need. 1 nitrogen atom and 3 hydrogen atoms. Step 1 is just the setup. We draw our circles, with each of the 3 hydrogens overlapping that main central nitrogen. Okay, now for the handshake part. Let's think. Nitrogen is in group 5, so wants to make 3 bonds. And hydrogen, it always makes 1. This is perfect. It works out exactly right. So we're going to place one shared pair of electrons, a dot from one and a cross from the other, in each of those 3 spots where they overlap. And just like that, you've got your 3 strong covalent bonds. We're so close. But wait, remember, a nitrogen atom started with 5 outer electrons, right? We've only used 3 of them in those bonds. So what about the last 2? Well, they just hang out on the nitrogen as what we call a non-bonding pair. Now, if you do the final count, nitrogen has a full outer shell of 8, and each little hydrogen has its full shell of 2. And there you have it, a complete, totally stable molecule. So we've seen atoms share 1 pair of electrons, but what if they need to share more? What happens then? Well, that's when you get even stronger handshakes. We're talking double and triple bonds. And this is where it gets really cool. Think about oxygen. An oxygen atom needs 2 electrons. So what does it do when it meets another oxygen atom? They share 2 pairs, forming a double bond. And nitrogen? It needs 3 electrons. So 2 nitrogen atoms get together and form a triple bond, sharing 3 whole pairs. These connections are ridiculously strong. Okay, but hold on. Here's a puzzle for you. If these covalent bonds are so incredibly strong, why are things like oxygen a gas and water a liquid at room temperature? Why do they melt and boil so easily? It kind of doesn't make sense, right? Well, to solve this mystery, we have to zoom out and look at the bigger picture. Okay, this is absolutely the most important part to get. There are 2 totally different kinds of forces going on here. You've got the super strong covalent bonds inside the molecules themselves, the atomic handshakes holding the atoms together. But then you have these way, way weaker forces between the separate molecules. We call them intermolecular forces. The analogy is perfect. Think of a crowd of people. Each person is shaking hands with someone else really, really firmly, but the people themselves are just kind of standing loosely next to each other in the crowd. And that is the secret. That's the whole key. When you melt ice to get water or boil water to get steam, you are not breaking those super strong covalent bonds inside the H2O molecules. You're not. all you're doing is giving the molecules just enough energy to overcome those weak little attractions between them, so they can start sliding past each other. And that's the takeaway, right there. It takes hardly any energy to nudge those molecules apart, because the forces holding them to each other are so weak. The actual strong covalent bonds, they stay completely untouched.
Just look at the numbers here. They tell the whole story. Oxygen melts at a crazy minus 218 degrees Celsius. That's because the forces between the molecules are just incredibly weak. Now, water's forces are a bit stronger, which is why it melts at a more familiar 0 degrees Celsius. But both of these are proof positive that you need very, very little energy to get these simple molecules to separate from each other. All right, one last property to tackle. We know they melt easily. But why don't these things conduct electricity? Turns out it all comes down to a question of charge. So for anything to conduct electricity, you need two things. It's a simple checklist. First, you need charged particles, like ions or electrons. And second, those particles have to be free to actually move around and carry a current. And simple molecules, they fail on both counts. Big time. The molecules themselves are neutral, no overall charge. And all their outer electrons, they're locked up tight in those covalent bonds. So you've got nothing charged and you've got nothing free to move, which means electricity has no way to flow. Simple as that. Which leads us to a really fascinating final thought. We've just spent all this time seeing how the properties of these simple substances are all about the weak forces between the molecules. But what would happen if there were no separate molecules at all? What if those super strong covalent bonds just kept on going, linking atom after atom after atom into one single giant structure? Well, that is a story for another explainer.